So this was known as a Holden
I
sphere.
screwed up really bad here on this.
And you get it spinning, but then this also shows, you talk about work, you talk about angular momentum, you talk about a whole bunch of different things. So if I want to make it spin, what do I have to do?
Work it.
Apply a torque, right? Okay? I have to apply a certain force over a distance. So if I do that, then I create angular momentum. So right now it has a certain amount of angular momentum. Now, what I'm going to do is I'm going to pull on the string, and that's going to collapse it. So as I collapse it, what's going to happen to the radius?
It's going to decrease.
It's going to decrease. To create the same angular momentum, what has to happen?
More forward.
It has to spin
Faster.
faster. So if I do that, oh, come on. Here we go. Spins faster, let it down. Spin slower. So same thing is true of like tornadoes. So as tornadoes, as you get closer to the center of the tornado, angular momentum has to be conserved. The closer you are, the faster it spins. Now the cool thing about this one is this one actually glows in the dark.
Ooh.
So you get it going. Hours of entertainment. Okay,
That's kind of cool.
it is kind of cool. It is kind of
Very
cool. So,
interesting.
What are you looking at? Got any practice?
okay,
Got any practice?
so let's talk about this concept of work. Oh, there's the assignment.
Oh, I need too many.
And there's the lecture notes.
Not that one.
Okay. So there's two general ideas that happen when you talk about work. First off, the equation itself is going to be force times distance, okay? So you have to have two criteria. You have to have a force and it has to act through a distance. So the equations themselves are fairly simple. So for example, if you get like on number 8, okay, where you're lifting up the bucket of dirt. So generally you're going to have two situations. Where you lift something, okay, when you're lifting something, the work that you're going to do is the weight times the height, okay? Sometimes you see that written as mgh. Wherever the mass is, times gravitational acceleration, times however high you lift it. Now, obviously, if you don't lift anything, you don't do any work, okay? So that's going to be one of the criteria. So today, you'll also see that work is also going to equal a change in energy. And we're going to have two broad classifications of energy: gravitational potential energy and kinetic energy. So when I lift something up, I'm changing or increasing that amount of gravitational potential energy, and the work that I do is equal to the change in that energy. Now, so let me give you a hint, because if 8a is wrong, everything's going to be wrong. So your answer to 8a should be something times 10 to the 5th, okay? Because you're going to take the weight of the bucket plus the weight of the dirt, but you got to find the weight of the dirt. To do that, you got to find the mass of the dirt. To find the mass of the dirt, you got to take the density of the soil times the volume of the soil to get the mass of the soil. Take the mass of the soil times g to get the weight of the soil. Add that to the weight of the bucket. Now, when you get to question number 10, what are the two most important words on question number 10? Constant velocity, right? So that means all of the forces are going to add up to 0. So this block, right, is which way is the block sliding? Down or up? Down. So the force in the direction of motion is defined as a positive value. The force in the opposite direction is going to be the negative value. Now, here's this block, right? Could a block, listen to me very carefully, could a block slide down a frictionless inclined plane at a constant velocity?
Yes.
No, can't happen.
Physics, huh?
Because as soon as you let go of it, what's the only force acting on it? Force parallel, right? And if that's the only force acting on it, you're going to be creating an imbalanced force, and you're going to accelerate. If you don't believe me, if we ever get like a big ice storm, try to slide down an off ramp at a constant velocity in an ice storm. Okay? Promise you, it is not going to happen. You will do nothing but accelerate going down that ramp because there's no frictional force to impede that motion. So the only way this thing can slide down at a constant velocity is if the frictional force is in the and has the same
Plus.
magnitude. So your answer to number 10 would make a horrible GPA. Okay? Your answer to number 9 should be something times 10 to the 4th. There's two ways you can do number 9. You can either take the force parallel and multiply that by the length of the escalator, or you take the weight of the president and multiply that by the vertical distance that he gets lifted. Okay, that's it. Those are the only two options. So it's either force parallel times the length, or FG times the height. And that's, we're just neglecting any considerations of friction on that one. On number 11, make sure that you have given me some type of mathematical justification for your answer, okay? You just can't say, oh, it has a bigger acceleration. Great, it does. Or it has a smaller acceleration. Great, it does. How does that translate into your answer? How does that translate into distance? How does that translate into momentum? How does that translate into work? Okay? So you just can't say, oh, it has a smaller mass and a greater acceleration. Cool. What does that mean? Okay? So keep that in mind. When you get to question number 2 on the problem number 2, problem number 2,
312.
both of your tensions, tension 1 and tension 2, should be something times 10 to the 3rd, and the overall weight should be something times 10 to the 4th. Okay? So tension 1, tension 2, they are not the same. Okay? They are not the same. Tension 1 is going to be bigger than tension 2. But one's going to be bigger than the other one. Tension 1 is going to be bigger. Because it's a bigger force, so multiplied by the same distance. And I'm talking about the work done by them, not the actual tensions themselves. I'm talking about the work being done by them. On number 6, your work should be, and this, I'm not telling you positive or negative, I'm just telling you the absolute value. On number 6, your work value should be between 200 to 300 joules.
What did you expect? Shop towels. Shop towels.
Sock towels?
But remember, on number 6, you only use the force that's in the direction of motion. Okay? You only use the force in the direction of motion. Okay. Any other questions?
Are you using this towel?
No. You can use it.
Dude, shop towels.
How the towel works.
This is a better towel.
You said boo?
Okay. Anything else? Going once, going twice? So, okay. So today we're going to start a journey on energy. Now, here's the anomaly about energy, okay? Is that I can pretty much gauge when you walk in the room how much energy you all have, okay? And some of you, it's pretty consistent, okay? Aspen's energy level, pretty always level, okay, right? Vanessa's fluctuates a little bit, like, this work camp versus, okay. So there's varies a little bit, okay? Louis, it's usually pretty level, okay? Becca was just pretty chill in the back, he's like,
And then there's Connor.
yeah. And there's Connor, like, "Rah!" Okay?
Just
So,
wanted to get up with his gummy bears.
so I can get a feel for your energy level that you all have. Okay, and the same thing with me. You can tell like, oh, Burkham's pretty high strung today, he's excited versus Burkham's maybe not feeling so well, he's
You can tell
old,
by the hair.
yeah, the hair, yeah, you can tell that by how much stress I had that day by my hair. So, but if I said, write a definition of energy. If I said, define energy, what would you say? Lou, if I said, give me a definition of energy, what would you say?
I would say the thing that makes other things work.
The thing that makes other things work. That's actually, there's a lot of validity to that, okay? So let's talk about the thing that makes the other things work. What's the thing that you put in your car to make the other thing work?
Gas.
Gasoline,
Oil.
right? That's the thing, right? Okay? So the thing is gasoline that you put in the car to make the car, which is the thing, work. True? Okay? What do you have to have in your phone to make it work?
A battery.
A battery. You have to charge it, right? Because if you don't have the thing, which is your charged battery, the thing doesn't work. True? Okay? So from a physics perspective, we define work as the capacity, we define energy as the capacity to do work. Okay? So if you go back to what Louis said, okay? You go to Quick Trip and you buy gasoline. Fundamentally, what are you buying?
Energy.
You're buying energy. Okay? You're buying energy stored in the chemical bonds within that chemical product. Okay? Now, why don't you fill up your car with gasoline? Why don't you fill it up with gasoline instead of water?
Because water doesn't blow
No
up,
heat.
combust, it doesn't combust.
Yeah, water doesn't have any stored potential energy in it. Okay? It's like the bottom of the energy well. Okay? Oh, let's run off water. It's a cool idea. Guess what? Water doesn't have very much potential energy stored in its bonds. It's a great substance, don't get me wrong, it just sucks as a fuel. So, let's say 6 o'clock on Saturday morning. Okay? Mom says, hey, Aunt Martha's coming over to the house. The house is a disaster. She's going to be really judgy. I don't want to deal with it. I need your help cleaning the house. And you go, Mom, I don't have the energy. Okay? So what, from a physics perspective, what you're telling your mom is that you do not have the capacity to do work.
Right.
She needs you to vacuum. And you're going, Mom, I do not have the capacity to exert a force through a distance and run the vacuum cleaner. That's what you're saying. Okay, if you say, I don't have the energy, you're saying, I do not have the capacity to do work. Your car runs out of gasoline. Can your car do work?
No.
No, because you don't have
Energy.
the capacity to do work. Okay? So if you look at energy, there's 2 broad classifications of energy. There is potential and kinetic. Now, with potential, we're eventually going to study 3 types of potential energy. The first one we're going to study is UG, okay, which is gravitational potential energy. So that's a very simple equation. It's just mgh, okay? So if I take a golf ball and I lift it up, I store a certain amount of potential energy. And that would be the mass of the object times the gravitational acceleration times the height. So if you look at the units, that the M is going to be in kilograms. And then you got, otherwise known as newtons times meters. Newton meters is the same thing as joules. So gravitational potential energy is stored in joules. We're also going to talk about us. And that isn't like the, oh, that's a relationship talk about us kind of thing. This is the physics that talk about us. Okay? And that's potential energy stored in a spring. So one way you could look at this is that this was a toy from a Happy Meal that somehow ended up in my room. I'm not sure. So I'm going to take this and I'm going to push this back. Okay? So I did work. I stored energy because I exerted a force over a distance. Now when I push the button, that potential energy that I stored in the spring turns into kinetic energy. Okay? Now, this K, which we'll talk about potential energy stored in the spring later, this K is what's known as your spring constant. And that has units of newtons per meter. Don't worry about this for now. We'll spend a whole day talking about this. I'm just laying this out. So that's newtons per meter. X is how far the spring gets compressed or stretched. So that's going to get squared. So I got newtons per meter times meters squared gets me Newton meters, otherwise known as joules. Okay, that's kind of cool. Then we can also talk about EUI, which is electrical potential energy, and we'll spend an entire 2 weeks talking about electrical potential energy. Okay, and oddly enough, that's also going to be stored in units of joules. Okay, so if you have figured out the recurring theme, all forms of energy is going to be stored in joules. Now, this is the one that impacts your life as a phone-owning member of the human race more than about anything. Because imagine, if you will, your life, if your phone only worked if it was plugged into the wall. Okay? Imagine if we did not have the capacity to develop batteries. Now, because purpose, yeah, you ought to be screaming like, grab my phone, plug it into the wall. Oh, good, okay? It's pretty big to plug in first. So imagine, if you will, what's the function of the battery in your car?
Hold the charge.
Store EUI, right? That's it. Okay? Anybody know how the first generations of cars were started?
Crank.
With their hands.
Crank, right? You were the battery. So you would take your crank, put that in the engine, and you would spin it. You were the battery. Okay? Now imagine it's cold outside. Okay? And it's snowing, right? And you got to go out there and you've got to crank your car. And then your battery, your phone won't work because it's not plugged in. It's like, can't call anybody because, I'm locked outside, the car won't start. Okay, right? So I'm just saying, imagine if how your life would be different if we didn't have the capacity to store electrical potential energy. That you would have no batteries in your car. You would have no batteries in your phone. We could develop the technology for cars. We could develop the technology for phones. But they would only work if they were plugged in. It's like, oh, that's not a pleasant thought. Okay. Now, when you get to kinetic energy, we're going to talk about two broad types. We're going to talk about KT, which stands for translational, and that's 1/2 mv squared. And then you can have rotational, which is 1/2 I omega squared. Okay, and if you think about it, you're multiplying together the same thing. Mass, resistance to a change in linear velocity. I, a resistance to a change in rotational motion. V is how fast you're moving. Omega is how fast you're spinning. Okay? So you're multiplying together the same thing. Now, let's talk about these. Do you think Kr and Kt are vector quantities or scalar quantities?
Vector,
Why?
because they have velocity, they have some sort of velocity.
It's true. Okay. So let's give that a spin. So if I take this weight and I lift it up, okay, did I just do work?
Yes.
No.
Why?
Force
you
in the
move-
direct
I exerted the force over a
Yes.
distance. Now at this point, I have stored gravitational potential energy, right? So when I let go of it, what's gonna happen?
Come back to
Fall.
you.
Why is it gonna fall? Because
Gravity.
Mother Nature likes
Kinetic.
kinetic and she doesn't like
Potential.
potential. So as soon as I let go of it, it's gonna begin to transform from potential energy into
Kinetic.
kinetic energy. Now, does it change direction?
Yes.
Yes.
So does the kinetic energy change sign?
Yes.
No.
No, because it's squared,
Oh, what'd you say, Devin?
because velocity is squared.
Velocity is squared. So does the velocity change sign?
No.
Yes.
Does the velocity
Oh.
vector change sign?
Yeah.
The velocity vector changes sign. Does the momentum vector change sign?
Yes.
Yes.
Yes, because momentum is mass times
Velocity.
velocity. But does my kinetic energy change sign?
No.
No.
No, because it's 1/2 m
Squared.
v squared. So even if you have negative velocity,
It's squared to
it's going to
positive.
get squared and it's going to become
Positive.
positive. Now, is it possible to change the amount of kinetic energy an object has?
Yes.
Yes.
Yeah, look at this. Does the kinetic energy change?
Yeah.
Yeah.
When does the kinetic energy go to zero?
When it's
Up there.
And
There.
Up there.
Back and back.
every time it
Back.
changes direction.
changes direction, because every time it changes direction, the velocity goes to
Zero.
zero. So when do you think it has its maximum kinetic energy?
At the bottom.
At the bottom. Does it have gravitational potential energy?
Yes.
Why? Oh, no.
There's 10.
Look at how you calculate gravitational potential energy. What three things do you multiply together?
Mass, gravity.
Oh, with
So
the
is it
bow.
in a gravitational field?
Yes.
Thank God. You really would if it didn't. Does it have a height?
Yeah.
Yes.
Yes. Does it have mass?
Yes.
Yes. Okay. Now, the higher I pull it, what's going to happen to the amount of energy that it's going to have?
Increase.
It's going to increase, right?
More
Okay.
velocity.
It's going to get bigger and bigger.
Yeah.
Now, I'm going to hold this thing up like this, right underneath my chin. I'm going to let go of it. Hold on. That didn't get a clean release. That's bad. So try that. So we like this, right?
Cool.
Now, why didn't I have to worry about it hitting me in the chin?
It loses velocity.
Yeah, it's going to lose a little bit because there's air resistance, right?
Yeah.
Even if there wasn't air resistance, if I let go of it, it still wouldn't hit me in the chin. Why?
Because it's losing some, or its energy is being transferred somehow.
Yeah, so one of the things you can talk about energy is that you can talk about it in terms of like containers. So imagine that we're going to have two containers. We're going to have an UG container and we're going to have a kinetic energy container, right? So when I lift that thing up, did I do work?
Yes.
And the work that I do is going to be stored as potential energy. So the work that I do is going to equal the change in my UG. Because I do work, that changes that. So I'm going to start with a certain amount of UG, right? And my kinetic energy container is going to be empty. Because I'm just holding it, right? So I lift this up. Now, interesting thing happens. Let's look at two different scenarios. Scenario number one, and give that a spin again. Scenario number one, I lift it up to the height of my chin and I drop it. Okay? So this is going to have a certain amount of energy because I did a certain amount of work. And as soon as I let go of it, what's going to happen to that UG? It's going to change into
Kinetic.
when it hits the bottom, right? Energy has to be conserved. Now, if I take that over here and I lift it to the exact same height and then I let go of it, what do you know about the velocity that it has when it swings here, from that height to here, versus if I just lift it to that height and drop it?
The same,
Why?
because what happens in the Y stays in the Y.
It's traveling the same,
Kinda.
it's traveling the same distance.
Okay,
No.
are any energy quantities vector quantities?
No.
They're all scalar, right? So if I lift this up to a certain height, I do a certain amount of work, I store a certain amount of UG. And when I let go of it, that UG is going to change into kinetic. So if I hold it up here, I still store the exact same amount of UG relative to that equilibrium point. So when I let go of it, that UG here is going to change into kinetic energy at the bottom. If I lift it up here and drop it, I still have the same amount of UG, which is going to change into the same amount of, but this is where your X and Y idea comes into it. So if I drop it, all of my velocity is going to be in the
Down.
Y direction.
vertical direction. If it swings this way, all of my velocity is going to be in the,
Horizontal.
but it's still going to, that vertical velocity here is going to be the same as my horizontal velocity that way, because I still have to have the same amount of energy.
Yeah.
That's where your X and Y comes into account. Okay? All right. So if you like this idea, initially my UG container is empty. Then as it falls, imagine that there's a siphon. And I'm going to siphon energy from the UG container over to the kinetic energy container. Okay? So at the bottom of that swing, what's going to happen to my UG container? It's going to be,
Empty.
and it's all going to be in the
Kinetic.
kinetic. Now, eventually, this thing is going to stop. Okay? I would like to let that go and come back an hour later and still swing back to the same height every time. So what happens is that there's the third container of thermal energy. Okay? That's what's energy lost to heat. That's what's energy is lost to sound. So as that's moving through our atmosphere, which is a cool thing that we have, there's some drag. It's encountering nitrogen and oxygen molecules. And it's heating up a little bit. Okay? And notice that they go, oh, it's hot. I feel it. No, no, no. Okay? An extreme case, though, is like when you have like a meteor or a spaceship that enters the Earth. It's going really, really fast and enters our atmosphere, and then it burns up because it is going so fast that it does create a tremendous amount of thermal energy. So that's going to stop, and then all that energy is eventually going to end up as thermal. Now, there's a couple of different ways you can view this transformation. So here we have E.T., old movie.
Oh, I like that.
And if I spin this up,
Is that an Easter egg basket?
they're flowers.
Oh.
Okay? If I spin this up, am I doing work?
Yes.
Yes.
Because I'm storing energy in
Spring.
the spring. Now, when I let go of it, the energy that I store is changing into kinetic. But you hear it, right? Okay? There's some little bit of friction between his feet. And so the cool thing about energy is that energy is conserved. This is one of the great conservation laws. So the only thing that happens in the energy in the universe is that the energy changes form. Okay? So what's the ultimate source of source of energy for me to wind up ET? What's the ultimate source of that energy? It's a big ball of light in the sky. Sun, right? Sun shines, the crops grow, I have a pancake for breakfast. Okay? Made from the wheat that took the energy from the sun and made wheat. We ground it into flour, I made a pancake, I had a pancake for breakfast. So my body is taking the energy that came from the sun that was stored in the flour that I consumed as food. And my body has the capacity to break those bonds and take that energy and make that available to me so I can wind up ET. Because the sun dries out, the sun goes away, whatever, stops shining, bad things are going to happen. Because guess what we've lost?
Energy.
Our source of energy. Okay? Without that, bad things are going to happen. We're going to get awfully cold, awfully dark, awfully fast.
Awfully dead.
Now, if you look at, on a bigger scale, okay, if you subscribe to the Big Bang, at some point there was what's called a singularity. All the mass, all the universe, all the mass, all the energy, even space and time, was condensed into one infinitely small point. Something happened, it erupted. And even though they call it the Big Bang, here's the anomaly: there was no bang because there was no sound. Okay, 'cause it just wasn't there. So space and time began to get formed. So the amount of energy and mass, and Einstein equated those two with his equation that E equals mc squared. Now, the beauty of this is that if you look at this, it had to be mc squared. Why did it have to be mc squared and not E equals mc? First off, what is c?
Meters per second.
Speed of light in meters per second. If Einstein's tried to say E equals mc, why would all the other physicists laugh at him and call him names?
Because you can have negative energy.
No.
Because the units wouldn't match up.
Yeah. mc is the same as mass times velocity. Well, what's mass times velocity?
Momentum.
Momentum. You can't say energy is mass times the speed of light. Okay, you can say momentum is mass times the speed of light. Okay. Now, look at the units. Mass is going to be in, c is going to be a velocity in, but that's going to get squared, so you get meters squared over, otherwise known as
Kilogram meter squared per second.
joules, otherwise known as joules. Okay? Wow, how cool is that?
And then,
Okay?
so what does that solve exactly? Like,
Basically, what this does, and we'll talk more about this when we get into the fourth 9 weeks. So what happens, here's the short version. Well, if you look at the sun right now, the sun is smashing together hydrogen and producing helium. So if you had a balance, and you put 4 hydrogen atoms on one side, and you put 1 helium atom on the other side, the 4 hydrogen atoms have a tiny bit more mass than the 1 helium atom does by itself. Okay, it's called binding energy. So what's happened is that in that process, we've lost some mass. Okay? That mass, that difference in mass between the 4 hydrogens and 1 helium is what goes into this equation. So when mass becomes energy, this tells you how much energy you get out of that transformation. Okay? Now, the weird thing
I thought
is
you
you
couldn't
can make the
destroy
door
mass,
swing
though.
the other way. If you have enough pure energy, you can make mass come out of that, which is what happened in the Big Bang. So at the beginning of the energy was just, the universe was just pure energy.
I thought you couldn't create or destroy mass.
You can't, but you can change the form between energy and mass. So initially there was just pure energy. Then as the universe expanded and cooled, then out of that energy you begin to get protons and electrons and neutrons. And then you begin to get gravitational fields, and then you began to form stars, and then you began to have the fusion process where hydrogen changed into helium, and then you began to see stars appear in the universe. But initially the universe was completely dark.
That makes sense.
It's a little bit weird. Okay. Now, so here's the odd thing. The amount of energy in the universe is constant, just changes form. So it's been theorized, and somebody had to be really bored, that if you could yell, "Ah!" like that, for about 8 hours, and if you could harness that energy, you would have about enough energy to make a pot of coffee.
Oh, it's like Monsters, Inc.
It is. It's the same idea. Okay? If you ever seen the movie Monsters, Inc., they harvest the energy in
Screens.
Little kids'
screens.
screens.
Okay? And they use that to power the town. So, and this is kind of a cool thing. It's like, okay, so I've been teaching in this room since the fall of 1996. Okay? 26 years now I've been teaching in this room. And there's been a lot of energy that's been inside this room. A lot of sounds, a lot of laughter, a few tears. Okay? But there's been a lot of energy in this room. And that energy still exists. It's just changed forms. Okay? So it's kind of a cosmic kind of connection, is that, especially as, as long as I've taught, it's like, okay, yeah, I've given of my energy. And hopefully some of, you guys, you go home and go, oh, I'm going to do the homework. So you're going to take some of that energy for me to do that homework. So that energy is just changing forms. So that's kind of the cool connection about this. So if you look at how different generations have been defined, okay? So quick historical lesson. So my dad was born in 1927, which is now out by Cheney Lake, small farm out there. And when Dad would come into Wichita, 21st Street was a set of wagon ruts. Okay, it wasn't a paved road, it wasn't even a road. A set of wagon ruts. So what they would do is they would hook up the wagon to the horses in the morning. It would take them all day to come into town, get whatever supplies that they needed in Wichita, and then go back. Okay, that was a day-long trip. So when Dad was born, that was transportation. You hooked up a wagon to the horses, and you came into town and went back. So Dad died in 96. So by the time Dad died in 96, he had seen jet travel. He had seen people walk on the moon, flew the ocean. And so my dad's generation saw a tremendous change in transportation, how you get from one place to the other. Now, my generation, born in 66, has seen a huge change in how information is moved from one place to the other. So when I was grade school, high school, whatever, okay, this is at the time what we call BC, which stands for before cell phones, okay? Yes, shocking as that is, there was a time before cell phones.
No way.
Now, even more shocking, there was one phone in the house. It was attached to the wall,
Landline.
landline, okay?
I have one of those.
And someone would call. First off, there was no caller ID. It was a mystery. Who's going to be there when you pick up the phone? You didn't know, okay? And if you wanted to talk to your friend, girlfriend, whatever, you had that conversation right there between mom and dad, because there was one phone in the house, and that was right there. And so this whole, oh, I need my privacy, whatever, shut up. You had a conversation with your mom and dad right there, okay? The whole concept of privacy did not exist. Worse yet, prior to that, I lived out in Cheney. So I lived out in Cheney through like 6th grade. And at the time, there was something called the party line. You know what the party line is? So what happened on the party line, number one is landline. You pick up the phone.
Oh, you have multiple.
And there were like 3 or 4 neighbors that shared that line. So when you picked up that phone, unless you got a dial tone, which is a completely foreign concept, but unless you got a dial tone, that means that you could realistically pick up that phone and you could listen in on other people's conversations. Okay? Or you always had to keep that in mind. If you were talking, your neighbors had the capacity to pick up the phone and listen in on your conversations. Okay? It's like, flipped out. Okay? It's like, oh, tough, right? So even like when I was in high school, you did research papers. Okay? Standard deal. Still, sophomores or juniors, you did the big research paper. Shocking as it may be, you actually went to the library and you got books off of the shelf. Okay? And you read the books.
No way.
And you turned the pages. Okay? And if you wanted a quote, you actually wrote it down. And then you went to a typewriter and then you like actually typed the words on the screen. Which showed them, actually wasn't on the screen, it was just on
Paper.
on the paper.
Yeah.
Okay, and if you made a mistake, you had to tear out the paper and start all over again. Okay? Shocking as that may be. Now, so my generation has seen a huge change in how we communicate. So I remember 4th grade, remember this distinctly. Mike did. Lived out in Chino. Used to be the phones were the old rotary dial. So if you wanted to dial a number, okay, like the number 5, you put your finger in the number 5 spot, roll it around, let go, okay? That's how you would dial numbers, okay? Manually hit that. So Mike Denny was the first kid that I ever knew that had a push button phone. And so I remember he said, I got a push button phone. No way. So after school, we all ran over to Mike Denny's house just so we could play with his phone and push the buttons on the phone. It was the coolest thing. Okay, and you always sitting there going, oh my God. But again, look at the times, okay? He had the first video game. Anybody know the first video game?
Duck Hunt.
Pong.
Pong, yeah.
Okay? Pong. And you had a little button, and you would turn it, and you would slide the little paddles up and down, and the ball would go boink, 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 boink. That's the first video game. It was the coolest thing. Mike Gandy was the envy of everybody because he had the first push-button phone and the first video game.
Was he rich?
No, not really, but his dad was a technical junkie, so his dad was big into it. So, now, I look at how my generation has changed in terms of communication. It was like the other night, I don't know I'm late to the party on this, but I was like doing math. I had to solve some stuff in Chem 1 class, and I just didn't feel like punching in my calculator. And I realized I could just ask my phone, it's like, hey, what's 5 plus 9? And the phone gives the answer, like, my God, I don't even have to type this thing into my phone anymore. I can just, on the calculator, I can just say, hey, what's 5 plus 9? And I get an answer, and it's right. So my generation has gone from looking up things in
Gotcha.
magazines to having access to the Library of Congress at the touch of my phone. So my generation has seen a huge change in
Technology.
communication. Now, here's what I hope your generation sees, okay? Your generation better see a big change, oddly enough, in energy. How you produce it, how you store it, how you access it. Because something's got to change, okay? You look at all the climate change models, and you know, people say, well, why'd you do the solar project, okay? The carbon dioxide reduction is a drop in the bucket, and it is. But this is like what's on the back of that T-shirt up there. And I remember it was John Cole. John Cole sat right there, kind of where Beckham is. And we were talking about it. I said, it's a drop in the bucket. And John was very realistic. He's realist. He goes, it's a drop in the bucket. And I said, you're right, John, it is. But it's my drop, and it's my bucket. And if enough people make a drop in a bucket, you fill up the bucket. Somebody's got to start making a drop in a bucket. And so that's why I did it. And so your generation, more and more, I hope the climate change models are wrong. I do.
Like the worst comes to worst.
You mean to play out your work here? You want my worst case scenario?
Yeah. Yeah.
Here's my worst case scenario. It actually is going to happen in the oceans.
Live on Mars.
In the oceans?
The oceans. Worst case scenario is going to happen in the oceans. Right now, the oceans work on a huge convection cycle, and the oceans are always being mixed. Okay, so you have cold water at the poles, and you have warm water at the equator. Okay, and that warm water at the equator goes along the surface. It hits the poles. It's cold. It sinks. It comes back down to the equator, and it's just one big convection cycle like this. Okay, but that only works with the temperature differential. You have to have enough of a temperature gradient between the poles and the equator. Right now we're losing that temperature gradient. If you ever lose that temperature gradient, you stop mixing the oceans. If you stop mixing the oceans become stagnant. So if you ever seen a pond in the summer,
Yeah.
what happens to the fish?
They die.
They die.
And it smells terrible.
It smells terrible. Look at how many people are fed out of the produce of the oceans. Gulf Stream goes from the Gulf of Mexico up past England. They've been monitoring the speed of the Gulf Stream. Okay, the Gulf Stream is as slow as it's ever been measured. And if you ever stop it, guess what? You can't start it up again. That's my worst case scenario, is that you stop the mixing of the nutrient cycle in the oceans.
What if we have another ice age after that?
Screw that one. That's not gonna make any difference.
No?
Nope. Not gonna make any difference. So what my fear is that you start what's called a negative feedback loop,
Yeah.
and that's what they're seeing now. So methane is actually a much more potent greenhouse gas than carbon dioxide is. So right now there's a tremendous amount of methane stored in the permafrost, like in Siberia and northern Canada, okay? Stores a tremendous amount of methane. But it's locked up because it's in permafrost, okay? Well, the poles, especially the northern pole, is warming up faster than we are at the equator. So what's happening is that permafrost is thawing out. As that permafrost thaws out, it's releasing methane gas. That was sequestered in there as permafrost. So now you start, this is this negative feedback loop. So, oh, the temperatures are warming, you're thawing out the permafrost. As you thaw out the permafrost releases huge amounts of methane gas. Methane gas gets into the atmosphere. Methane gas acts as a very potent greenhouse gas. It traps more energy. It traps more energy, temperature rises more, you melt more and more permafrost, you release more and more methane into the atmosphere. That's my fear, are these huge negative feedback loops. And once you start them, you can't stop them. So there's my worst case scenario, right there. Then you also get into, then polar ice caps melt. Well, everybody says, oh, what's so bad? The ice is already in the ocean. No, it's not. This is ice that is on land that would melt and go into the oceans. So one scenario is that, like, here's Florida. All of that of Florida goes underwater.
New Orleans is gone too.
Yeah, that's okay. It's New Orleans.
I like New Orleans.
God hates New Orleans, really. And who can blame me? So, I'm just saying.
There's witches.
I know. It's like, they do. So that's my fear. So hopefully your generation is smart enough to let government officials that actually believe in science and don't use global warming as a political situation. Like, oh, it's not true. And I was like, and this is what I tell people with the solar projects. They're like, okay, worst case scenario, the climate change models are wrong. Fine, I hope, great, we're wrong. We still save $50,000 a year in electricity costs. Okay, I'm wrong. Cool, we're saving $50,000, big deal, okay? So, anyway. Earthquakes, which never used to be something that we would experience here in Kansas. How are earthquakes an example of energy?
The
It's
tectonic plates.
Tectonic plates.
Yeah, what about them?
They rub against each other and
Yeah.
make vibrations.
Yeah, so it's like taking this string, right, okay, and I pull it hard enough, what's gonna happen?
Snaps.
It's gonna snap. What happens to that potential energy? It changes into kinetic energy. So all earthquakes are is transformation from potential energy into kinetic energy. Okay, so, Louis, catch this? Okay? Now, when I threw that ball to Louis, did I do work?
Yes,
Yes.
Why?
because it was a
Force
force in the
inertia.
direction of motion.
I gave a force over a distance. Did I change the kinetic energy of the ball?
Yes,
Yes, because it was the initial kinetic energy of the ball.
zero.
Zero. Well, let go and have a certain amount of kinetic energy, right?
Yeah.
Did Louis do work on the ball?
No.
Sure he did.
Yeah.
Well, it
When
was,
you caught it,
yeah.
did you do work?
An opposing
Yeah.
force.
You work to slow it down.
I
Did you
but
exert
it
a
wasn't-
force over a distance?
I did,
You did. Did you do work?
yeah,
Did you change the kinetic energy of the ball?
yes.
Yes.
Wait, so I thought it had to be in the direction of travel.
No,
Yeah.
no. That's if it's positive work. Work can be
Oh,
negative.
you do negative work.
If you do negative work, you're in the
Opposite.
opposite direction of motion. So I did positive work because I increased the kinetic energy of the ball. You did negative work because you decreased the kinetic energy
So
of the ball.
always has to
Okay, now throw that back. Now, what if I don't catch it?
Then the floor does negative work.
What if I don't exert a force, guess what? The kinetic energy doesn't change. Now, we're getting into a whole bunch of equalities here. So, work can equal force times distance, which can also equal a change in energy. And that energy could be anything. It could be UI, it could be UG, it could be KR, it could be KT, it could be us. Okay? It's a generic change in energy. So if you're talking about kinetic energy, there's a whole bunch of different ways you can write this. You can write this K minus K naught. You can write it as 1/2 mv squared minus 1/2 m v naught squared. you can write it as 1/2 m times v squared minus v naught squared. Now, can kinetic energy itself be a negative value? No. But can you have a negative change in kinetic energy?
Yes.
All day long, okay? So here's the deal. So since change in kinetic energy equals work, which equals force times distance, so if you look at what I did, I increased the kinetic energy of the ball, right? I took it from 0 up to a positive value. Louis took the ball from a positive velocity to 0. So I did positive work because I increased the kinetic energy. Louis did negative work because he decreased the kinetic energy. So kinetic energy itself can't be negative, but the change can be negative. Big difference. Now, is it possible for a ball to have both potential energy and kinetic energy at the same time?
Yes.
How, Vanessa?
Well, like if you drop something, it still has a height, but it's still moving, so it's kinetic.
Yeah, so if I drop this, as it falls, what happens to the amount of UG, gravitational potential energy?
Decreases.
UG becomes,
Smaller.
but my kinetic energy becomes
Bigger.
What if I throw this to Louis, okay? As I throw it, did it have both? Yes, because it had kinetic energy because it was moving, and it had UG because it was falling. Now, throw that back. So what's the only way I could get this to Louis, but only have UG? Excuse me, only have kinetic energy and no UG?
There's no
Roll it?
You have to roll it across the floor.
Yeah, if I rolled it to him on the ground.
No height and
So if I rolled it to him along the ground, that would only have
I mean,
Kinetic.
kinetic with no UG. But as long as it's above the air, it's going to have both. Okay? Got that idea. So stop y'all the camera. Okay. So some of these are going to have to go old school. So when you get to like number 9, planets travel in elliptical orbits, law of conservation of energy must be followed, explain changes in potential energy. The planet goes from its furthest from the sun to the point where it's closest. So here's the deal. So you can think of that as being like the container analogy. So what do you know about a planet when it's furthest from the sun? Does that when it's had its highest velocity or its lowest velocity? When it's furthest away,
highest. Wait, no.
Oh,
Slowest.
right? That's when it's going slowest. Law of equal areas and equal time. Kepler's laws, right?
Yeah.
So when you increase, so you can think of that as like stretching the rubber band. So when that planet is at its furthest point, you've stretched that rubber band and you stored potential energy. Then as it goes around, it's going to slingshot around, and that potential energy is going to change into,
Kinetic.
that's why it goes fastest when you are closest to it. Okay? So keep that in mind. When you get to number 10, there's a couple of ways you can do number 10. You can go old school F equals ma, and then roll that into your kinematic equations. But at the end of the day, you have to figure out how fast the ball is moving, because you want to find kinetic energy. Or you could go old school, force times time equals change in momentum, which is mass times V minus V naught. You're going to do the same math, you're just going to change the sequence. So you can either go old school F equals ma, or new school force times time equals change in momentum. It's up to you. When you get to number 11, okay, when you get to number 11, do not be surprised if you have the same answer again and again, because the first thing you want to find is the work, okay? So you have the force and you have the distance. There's your work. Then the change in the kinetic energy. Well, what does work equal? Change in the kinetic energy,
Yeah.
okay? Then you want to find the final kinetic energy of the train. What do you think the initial kinetic energy of the train is?
Zero.
Zero, because the train starts at rest and it speeds up. Okay? So don't be afraid to get the same answer again and again and again. Now, on all of these, we're assuming that mass is constant. Okay? So don't get tricky and go, well, the velocity could be the same and we're going to change the mass. No. Stop. Don't be, no. Okay? Mass is going to stay constant unless I specifically tell you differently. Okay? All right, I'm done. You're on your own.